When you've completed this topic, you will be able to recognize the recommended troubleshooting guidelines, read electrical schematics, recognize 4 common electrical faults and their symbols. When you have completed this segment, you will be able to identify the 4 guidelines relevant to diagnostic troubleshooting. Describe the relationship between the 4 electrical systems in Caterpillar machines as they relate to the troubleshooting process. A solid understanding of troubleshooting guidelines will help you diagnose problems accurately and efficiently. The troubleshooting process typically happens in 4 stages. Following the stages will help you make the most of your troubleshooting time and efforts. These stages are: discover what others know about the problem. Discover what the machine can tell you about the problem. Think logically about the problem. Identify as many possible causes of the problem as you can. Make measurements. Let each measurement be an additional piece of information with which to reason with the problem again until you know the root cause of the problem. Discover what others know about the problem. Find out as much as you can about the problem from others. Good interviewing skills are important. You need to know how to ask questions and what questions to ask. In addition to obvious questions like what happened, you may want to ask, when did the problem occur? How was the machine being used? Was everything else working all right? What repairs have been made in the past? In the case of intermittent faults that happen off and on, questions like, what were the weather conditions at the time the problem occurred, can not only help you determine when the fault occurs, but a possible cause as well. For example, an electrical system that fails to work only when it rains can be an indication that moisture is creating unwanted current paths in the circuit. Discover what the machine can tell you about the problem. Observe the situation and, if possible, the operation of the machine. Check the accuracy of the information you have been given. Take a good look at the machine and see if there are any visual signs of the problem. For example, corrosion on any component of an electrical system can be an indication of where to begin to look for the cause of a problem, particularly if the component is part of the problem circuit. Listen to the sounds the machine makes. As an example, the click of a relay indicates that the electromagnetic coil in the relay is functioning correctly. It does not, however, say anything about the condition of the contacts in the relay. You can learn something about the problem by listening. You can even use your sense of smell. For example, the smell of a burnt part in the machine can indicate a short-to-ground fault. Identify as many possible causes of the problem as you can. Combine the information you have gathered with what you know about the system. How should the system work? How does the system work? If you need additional information, obtain it. Use this information and simple logic to narrow down the problem. Are there some things you know it cannot be, and other things you know it can be? Try to come up with some logical guesses about the causes of the problem. Identify as many possible causes of the problem as you can. Then ask yourself how you can prove your theories. For example, if the engine is slow to crank, it could be due to the state of charge of the batteries. You could perform an open circuit voltage test to determine the state of charge. Let each measurement be an additional piece of information with which to reason about the problem again until you know the root cause of the problem. Allow the conclusions you draw from the first 3 stages to direct how and where you use your diagnostic tools. Let each measurement you take be an additional piece of information and reason with the problem again. If the information gained by the measurement is helpful but not conclusive, ask yourself if there is a second test you can perform to prove that you have discovered the cause of the problem. For example, a voltage drop measurement across a switch may prove that a resistance exists, but is it definitely in the switch? Could it be the connection to the switch? A resistance measurement with the wires disconnected from the switch might be a good way to prove this. Use these kinds of opportunities to gain greater confidence in yourself, reinforce your knowledge of the way electrical circuits work, and prove to yourself that you know what the problem is. Be cautious. Ask yourself if the tests you have performed point to the root cause of the problem. For example, if the open circuit voltage test shows that the batteries have a low state of charge, why have the batteries lost their charge? Maybe the operator left a dome light on overnight. The 4 steps just discussed form the general outline of a good troubleshooting procedure. Discover what others know about the problem. Discover what the machine can tell you about the problem. Think logically about the problem. Make measurements. Make a conscious effort to follow these guidelines until they become second nature to you. Do not miss opportunities to take a second measurement or ask the customer or operator additional questions. Satisfy yourself that you have really found the root cause of the problem. When you complete this segment, you will be able to identify schematics and other publications as sources of information relevant to diagnostic troubleshooting. Distinguish between the color coding used in Caterpillar schematics and that used in Caterpillar wiring identification system. Identify the 3 elements, number, color, gauge, used in the Caterpillar wiring identification system. Service technicians would not think of trying to do their job without the proper tools. 2 essential tools for successful troubleshooting are the Caterpillar service manuals and schematics. Caterpillar service manuals are a guide for your service activities. Each manual is made up of several modules. The modules cover such information as specifications on machine systems and components, how each system works, how to operate and maintain the machine, how to test, adjust, assemble, and disassemble components, how to troubleshoot various machine systems. Whatever Caterpillar machine you are working on, the service manual can provide valuable information before you begin and during your work. Electrical schematics are part of the service manuals and include an index for all circuits in the machine, a location index for all schematic components and harness connections, switch, fuse, and circuit breaker specifications, diagrams of component and harness connector locations, wire identification information. Schematics are one of the most valuable aids a service technician can use in troubleshooting Caterpillar electrical systems. The wire colors you see on a Caterpillar schematic and the wire colors you see on actual wires in a Caterpillar machine have different meanings. When using a schematic that shows all of the system circuits in a machine, service technicians sometimes trace the outline of the circuit they are working on with a colored pen or pencil. Tracing a single system at a time helps their eyes stay focused on that one circuit while they work. The wire colors on the schematic are explained by a color key on the schematic. An individual color may indicate the status of a circuit under a particular condition or may identify the circuit. For example, all red wires on this schematic have voltage when the disconnect switch is on and the key switch is off. All black wires on this schematic go to ground, the vehicle frame. All gold wires on this schematic are part of the starting circuit. All wire colors on Caterpillar schematics for all machines have the same meaning. Red always indicates a circuit that has voltage when the disconnect switch is on and the key switch is off. Wire colors on the wires themselves in Caterpillar machines have a different meaning from the wire colors on a schematic. The wire colors you see while you are working on a machine are there to help you trace circuits on the machine. Sometimes wire colors are repeated, and you may sometimes have difficulty telling one color from another. For these reasons, wires are identified not only by color, but also by a circuit number. A circuit identification number appears on almost every wire. In addition to wire color, you can use this number to help you trace circuits on a machine. You can match the wire identification number on one end of the wire to the number on the other end of the wire as you trace it. For example, you may begin work on the electronic monitoring system coolant flow sensor circuit that runs from the cooling system to the cab. Wires in this circuit are colored blue. The circuit wires are hidden from view in some places, but by tracing the blue-colored wires to the EMS panel in the cab, you can identify the coolant flow sensor circuit. The schematic will identify almost every wire with a circuit identification number, a color code, and the gauge size of the wire when it is not 16-gauge wire. For example, the rear flood lamp circuit is identified on the schematic as 608-GN-14. The corresponding wire on the machine will be a 14-gauge green wire imprinted with the number 608. The circuit identification number for a wire is the same whether you're looking at it on a schematic or on a machine. Even though the wire colors on a schematic have a different meaning than the colors on the actual wires themselves, the circuit identification numbers are the same. When you have completed this segment, you will be able to define open as a fault condition, define short as a fault condition, define short to ground as a fault condition. Recognize examples of the three basic electrical faults as they might typically occur in CAT machines. Describe intermittent faults in CAT electrical circuits. Describe the procedure for troubleshooting intermittent faults in a CAT electrical system. Electrical faults can be classified as open circuit, resistive circuit, short circuit, or short-to-ground circuit. Understanding these faults and their effects is important in troubleshooting. An open circuit fault is a break in the intended path for electrical current. A resistive circuit fault is an unintended resistance in the intended path for electrical current. A short circuit fault is an unintended electrical connection that provides an additional path for the flow of electrical current. A short-to-ground circuit fault is an unintended path for electrical current back to the source of the electrical energy. A circuit is a path for the flow of electrical current. The conductors and devices that make up this path direct the current in a circular fashion, starting and ending at the source of electrical energy. In this circuit, for example, current flows from the positive, plus, battery post, back to the negative, minus, battery post. When an open occurs, the path for the current flow is broken. As a result, current can no longer flow. An open in the series part of this circuit will result in a loss of current flow to the whole circuit. This open has stopped all current flow through the circuit. Normally, a voltage drop measurement across the conductor from test point 2 to test point 3 would read 0 volts. In this case, the measurement will read system voltage. An open in the parallel part of this circuit will result in the loss of current flow only to the part of the circuit where the open occurs. Notice that current no longer flows through the part of the circuit where the open has occurred, but continues to flow through the rest of the circuit. The new circuit has more resistance than the original circuit and draws less current. Recall that the resistance of two resistors in parallel is less than that of either of the two resistors alone. Normally, a voltage drop measurement across the conductor from test point 2 to test point 3 would be 0 volts. In this case, the measurement will read a voltage because the digital multimeter will complete the circuit. Examples of opens in a CAT electrical system include a broken wire, a blown fuse or tripped circuit breaker, a harness connection with a corroded pin or socket. A circuit is a path for the flow of electrical current. To work properly, circuits must offer little or no resistance to the flow of current, except where resistance is intended. A resistive fault is an unintended resistance in a circuit sufficiently great to prevent the circuit from functioning normally. The amount of resistance circuits will tolerate and still work properly varies greatly depending on the circuit. For example, a starting circuit requires extremely low resistance due to its very high current requirements. Adding 0.1 ohm to such a circuit could cause it to fail. An electronic monitoring system sensor circuit can tolerate up to 500 ohms of series resistance and still work properly. This resistance adds to the total resistance of the circuit. Normally, a voltage drop reading from test point 2 to test point 3 would be 0 volts. In this case, the voltage drop would be a value greater than 0 and less than system voltage in direct proportion to the amount of resistance added to the total resistance of the circuit. Examples of resistances in a CAT electrical system include a corroded battery connection that causes the engine not to crank, a switch with burned contacts, a corroded connector. The ability of electrical circuits to direct, control, and use electrical energy depends on the way their components are connected together. A short is an unintended electrical connection within a circuit. It provides an unwanted path for current flow, one that can prevent the circuit from functioning normally. The short in this circuit provides a path for electrical current that bypasses the switch. As a result, the switch no longer controls the circuit. Because a short is an unwanted or incorrectly added connection, it often creates a circuit that draws more current than expected. This short allows the current to bypass resistor R1. Normally, a voltage drop measurement across the resistor from test point 1 to test point 2 would be a voltage between 0 and system voltage, in direct proportion to the ratio of the resistance of R1 to the total resistance of the circuit. In this case, the meter will read 0 volts. Examples of shorts in a CAT electrical system include a pinched harness, a burned-out starter solenoid. The ability of electrical circuits to direct, control, and use electrical energy depends on the way their components are connected together. A short to ground is an unintended electrical connection to ground within a circuit. It provides an unwanted path for current flow, one that can prevent the circuit from functioning normally. The short to ground in this circuit provides a path for electrical current that bypasses the resistor. The resulting increased current through the circuit breaker causes it to trip. This short to ground creates a circuit that allows the current to bypass resistors R2 and R3. Depending on the resistive value of R1 and the current rating of the circuit breaker, the current draw of the new circuit may be enough to trip the circuit breaker or burn out resistor R1. Normally, the voltage drop across resistor R1 from test point 1 to test point 2 would be a voltage between 0 and system voltage in direct proportion to the ratio of the resistance of R1 to the total resistance of the circuit. In this case, the measurement will be 0 volts if the circuit breaker tripped and system voltage if the circuit breaker did not trip or the resistor R1 burned out. Examples of shorts to ground in a cat electrical system include corrosion causing a direct path to the machine frame, a harness whose insulation is worn away by rubbing against the machine frame and makes direct contact with the frame. What happens when opens, resistances, shorts, and shorts to ground occur erratically? Intermittent faults, now you see them, now you don't, can be difficult to troubleshoot. Any electrical system or component that sometimes works and sometimes does not is an example of a symptom of an intermittent fault. These symptoms are not evident at all times and may not be evident when you arrive on the job to work on a system. You may therefore have to rely on reports from the machine operator to help you gather information about the fault. There is no specific procedure for troubleshooting an intermittent fault. As with any diagnostic troubleshooting, you should gather information on the problem, analyze the information, test the system, and make the diagnosis. One method you may want to use to expose intermittent faults is to wiggle various parts of the wire harness while looking for symptoms of the fault. When you have completed this topic, you will be able to perform diagnostic tests on batteries and be able to inspect them. When you have completed this segment, you will be able to describe the external characteristics of a conventional, low-maintenance, and maintenance-free battery. Describe the watering, cleaning, and dating requirements of a conventional, low-maintenance, and maintenance-free battery. Describe the consequences and restrictions of mixing different battery types. State the visual clues used in determining a battery's condition. There are 3 types of batteries you may find in Caterpillar machines. Each has some unique characteristics, but cleaning and determining the date of purchase is the same for all. Conventional batteries have no unique external characteristics. If you do not see the words low maintenance, high output, or maintenance-free on a battery, then it is probably a conventional battery. Conventional batteries lose a lot of water during charging. You should check the level of the fluid, electrolyte, in the battery on a regular basis after approximately every 100 hours of operation. Warning: avoid contact with the electrolyte. It is diluted sulfuric acid which can destroy clothing and burn the skin. Check the electrolyte level in all cells using the electrolyte level indicator if there is one. If not, as a rule, the electrolyte should be 1/4 inch to 1/2 inch above the plates in all cells. If the electrolyte level is low, add clean water. Drinking water is acceptable, but distilled water is best. Hard water is heavy in mineral content and can shorten battery life. Do not overfill a battery because this may cause the fluid in the cells to splash up and may cause injuries. Overfilling can also cause an imbalance in electrolyte content and cause corrosion of adjacent metal parts. After water has been added, the battery should be charged. Warning: be sure to replace the vent caps before charging. They are safety caps and can prevent explosion. The low-maintenance, high-output batteries have this name printed on the cover. Low-maintenance, high-output batteries lose water at a much slower rate than conventional batteries. You should check the level of the fluid, electrolyte, in the battery every 250 hours or so. Avoid contact with the electrolyte. It is diluted sulfuric acid which can destroy clothing and burn the skin. The procedure for adding water to the low-maintenance high-output battery electrolyte is the same as the procedure for adding water to the conventional battery. Maintenance-free batteries have this name printed on the cover. The cover and casing are completely closed with no access to the electrolyte for testing. Maintenance-free batteries therefore do not require inspection for electrolyte level. Maintenance-free batteries are vented, however, and should always be positioned upright to prevent leakage of the electrolyte inside. The cleaning procedure for all batteries is the same. The top of the battery should always be kept clean. Dirt and moisture can cause corrosion and short circuits and make the battery difficult to handle. Use a mixture of baking soda and water or ammonia and water as a cleaning solution. Mix 100 grams, 3.5 ounces, of either compound with 1 liter, 0.26 gallon, of clean water to form the solution. If necessary, use sandpaper to clean the terminals. When you finish cleaning the battery, wipe or rinse it with clean cold water. Use a wire brush as necessary to remove rust and corrosion from various metal parts such as the battery box and hold-down assembly. A battery's date of purchase provides a fairly good indication of how long the battery has been in use. The month and year of purchase are usually indicated on a label located somewhere on the battery. This date can be used to determine how old the battery is and if the warranty is still active. The 3 factors that influence battery life in CAT equipment are vibration, temperature, state of charge. Normally, a battery can be expected to last 4 years. In high vibration or high temperature environments, the life is cut approximately in half. Also, if you allow a battery to remain in a discharged condition for a month or longer, it may sulfate and fail to recharge. Sulfation is when whitish crystals form on the battery plates, lessening the battery's ability to store and deliver electricity. Battery life expectancy in service is the primary consideration for replacement. A strict first-in, first-out procedure, along with a date stamp for in service, records the information needed to support warranty claims. Caterpillar does not recommend mixing or chaining batteries of different construction. The different constructions require different charging voltages for each battery type. In a 24-volt system with mixed batteries, one battery becomes overcharged and experiences excessive gassing, while the other never receives a full charge. This shortens battery life. Notice, in 24-volt systems, do not use a maintenance-free battery with any other type of battery. The life expectancy of these batteries will be shortened when they are charged. Sometimes the visual appearance of a battery can tell you the reason for its poor performance. Corrosion around the terminals may be causing poor contact between the terminal and the battery cable. If a battery appears to be in poor condition, it may need to be cleaned or replaced. You should inspect the outside of the battery for damaged terminals and leaky or broken case or cover. Any of these faults are cause for battery replacement. You should also try to determine the reason for the damage before installing a new battery. When you have completed this segment, you will be able to describe the Caterpillar recommended procedure for jump-starting a battery. Some Caterpillar products are equipped with a jump-start receptacle as standard equipment. When a vehicle is equipped with a receptacle, you can use an emergency start cable, left. When a vehicle is not equipped with a receptacle, you can use standard jumper cables, right. The procedure for using the emergency start cable and the procedure for using standard jumper cables are very similar. Before you jump-start any machine, determine why it will not crank. Always use a voltage source equal to the voltage required in the machine you jump-start. Following is the procedure to jump-start the engine using an emergency start cable. 1. Place the transmission control in neutral on the stalled machine. Engage the parking secondary brake. Lower any attachment to the ground. Move all controls to hold. 2. Turn the start switch to off on the stalled machine. Turn off all accessories. 3. Turn on, close, the disconnect switch, if there is one, on the stalled machine. 4. Make sure the batteries in the stalled machine are not frozen. Make sure the electrolyte is above the plates in the cells. Make sure battery caps are all in place and tight on both machines. 5. Move the jump start source machine near enough to the stalled machine for the cables to reach. Do not allow the machines to touch. 6. Stop the engine on the jump source machine, or, if using an auxiliary power source, turn off the charging system on the auxiliary power source. If both the jump source and the stalled machine are equipped with a Caterpillar emergency start system, 7. Connect the appropriate jump start cable to the jump start receptacle on the stalled machine. 8. Connect the other end of this cable to the jump start receptacle of the jump source. 9. Start the engine on the jump source machine, or energize the charging system on the auxiliary power source. 10. Wait a minimum of 2 minutes for the batteries in the stalled machine to partially charge. 11. Attempt to start the stalled engine. If necessary, refer to the beginning of Engine Starting in the Operation and Maintenance Manual. 12. Immediately after starting the stalled engine, disconnect the jump start cable from the jump source. 13. Disconnect the other end of this cable from the stalled machine. Following is the procedure to jump-start the engine using standard jumper cables. 1. Place the transmission control in neutral on the stalled machine. Engage the parking secondary brake. Lower any attachment to the ground. Move all controls to hold. 2. Turn the start switch to off on the stalled machine. Turn off all accessories. 3. Turn on, close, the disconnect switch, if there is one on the stalled machine. 4. Make sure the batteries in the stalled machine are not frozen. Make sure the electrolyte is above the plates in the cells. Make sure battery caps are all in place and tight on both machines. 5. Move the jump start source machine near enough to the stalled machine for the cables to reach. Do not allow the machines to touch. 6. Stop the engine on the jump source machine, or if using an auxiliary power source, turn off the charging system on the auxiliary power source. 7. Connect the positive, plus, jumper cable, red, to the positive, plus, cable terminal of the discharged battery or battery set on the stalled machine. Do not allow positive cable clamps to touch any metal other than the battery terminals. Note, batteries in series may be located in separate compartments. Use the terminal connected to the starter solenoid, normally on the same side of the machine, as the starter. Note, on machines with 2 sets of 2 batteries, 2 in each fender, 4 total, connect to either set. 8. Connect the other end of this positive jumper cable, red, to the positive, plus, terminal of the jump source battery. 9. Connect one end of the negative jumper cable, black, to the negative, minus terminal of the jump source as follows. 12-volt systems. Use the negative, minus terminal of the jump battery. 24-volt systems. Use the jump battery negative, minus terminal, connected to the disconnect switch, in the same battery set used in step 8. 10. Make the final connection of the negative minus cable to the starter negative post of the stalled machine, not the battery negative post. Exceptions to this rule follow. If a battery cable size connection exists from starter negative post to frame, connect the negative minus cable to the frame of the stalled machine away from batteries, fuel, or hydraulic lines or moving parts. If the starter does not have a negative post, connect the negative minus cable to the engine block away from batteries, fuel, or hydraulic lines or moving parts. Start the engine on the jump source machine or energize the charging system on the auxiliary power source. 12. Wait a minimum of 2 minutes for the batteries in the stalled machine to partially charge. 13. Attempt to start the stalled machine. Refer to the section on engine starting in the Operation and Maintenance Manual. 14. Immediately after starting the stalled engine, disconnect the jumper cables in reverse order. When you have completed this segment, you will be able to state the conditions under which battery testing is recommended. Identify the recommended procedure for testing the state of charge or condition of a battery. State the procedure for removing surface charge prior to testing the battery. State the procedure for using a DMM to perform an open circuit voltage test. State the recommended procedure for testing the state of charge of a battery. The state of charge test has 3 steps. Inspect the battery and check electrolyte levels. Measure the open circuit voltage, OCV, of the battery. If the OCV of the battery is less than the minimum per the chart shown here, charge the battery. If the OCV is equal to or more than nominal voltage of the battery, remove the surface charge from the battery and repeat the OCV measurement. If this OCV is less than the minimum per the chart shown here, charge the battery. When a machine malfunction indicates that a battery may be the source of the problem, the first step is to examine the battery for dirt, corrosion, and physical damage, and check and correct the electrolyte levels as necessary. The top surface of the battery and the battery posts should be kept clean to prevent electrical current leakage paths. Damaged battery posts, a leaking or broken case, and a leaking or broken cover are all cause for battery replacement. After you have completed this step, continue with step 2 of the state of charge test. The open circuit voltage of a battery is the voltage of the battery when it is not delivering or receiving electricity. When measuring the open circuit voltage of a battery, use a digital type voltmeter to ensure the required accuracy. To measure the open circuit voltage of a battery, open the battery disconnect switch. Set the meter to the 20-volt DC setting and touch the probes to the battery posts. Any reading less than 12.40 volts on a 12-volt battery means the battery needs charging. Any reading equal to or more than 12.40 volts on a 12-volt battery means you should continue with step 3 of the state of charge test. The surface charge is a voltage resulting from the charging cycle. Surface charge gives a false indication of a battery's true state of charge and must be removed to obtain a true open circuit voltage measurement. To remove the surface charge, crank the engine for about 5 seconds with the fuel shut off, or turn on the headlights for about 1 minute. Then wait approximately 5 minutes for the battery to stabilize and repeat the open circuit voltage measurement. Any reading less than 12.40 volts on a 12-volt battery means the battery needs charging. When you have completed this segment, you will be able to state the conditions under which battery charging is necessary. Describe the relationship between battery voltage, battery type, and charging rate. Describe the approved procedure for correctly charging the battery. Before charging a battery, you should perform a battery state of charge test to determine if the battery needs charging. If the result of the battery state of charge test is an open circuit voltage less than the minimum per the specifications below, charge the battery. 12-volt battery. Minimum OCV, 12.40 volts. 8-volt battery. Minimum OCV, 8.27 volts. 6-volt battery. Minimum OCV, 6.20 volts. Before charging a battery, determine the correct charging rate and time and the maximum charging voltage for the battery. The rates and times shown in the charts shown here should charge a battery to the level required for load testing. The amp-hour rating of the battery determines charging rate. Open circuit voltage, OCV, determines charging time. The battery's rated voltage determines maximum charging voltage. Demonstrated on this chart, for example, is a 150 amp-hour 12-volt battery whose OCV is 12.25 volts, yellow boxes. This battery should be charged at the rate of 25 amps for 2 hours, and the maximum charging voltage allowed is 16.00 volts, red boxes. To view a full-size PDF of the chart, select the View Document icon on the navigation bar. Charging the battery is a 3-part procedure. Prepare the battery for charging. Prepare the battery charger. Charge the battery at the correct charging rate. 1. If the battery is a conventional or low-maintenance high-output type, make sure the electrolyte is above the plates in each cell. It does not need to be up to the filler neck, but only above the plates. 2. Make sure the battery is not frozen. 3. Do not attempt to charge a battery that has ice in any of the cells. Charging a battery in this condition can cause an explosion. 4. Always let the ice melt before attempting to charge the battery. 5. When charging batteries, the battery vent caps must be installed. 6. Do not attempt to charge a battery with the vent caps missing. These vent caps have built-in flame arresters that reduce the possibility of external sparks igniting the battery gases. 7. If you're going to charge the battery in the machine, disconnect the cables from the battery. 8. Do not attempt to charge more than one battery at a time. 1. Be sure the charger is off when you connect it to the battery. 2. Adjust the charger to match the battery's rated voltage, in this case 12 volts for the 12-volt battery. 3. Connect the red charger lead to the positive terminal post of the battery and then the black charger lead to the negative battery terminal post. 4. Make sure the clips are securely connected. 1. Turn on the battery charger and set the correct charge rate for the battery, using the amp-hour rating from a battery charging rate timetable. 2. Observe the battery's terminal post voltage during charging. 3. The battery's terminal post voltage should never exceed the maximum for the rated voltage of the battery, except during the first 15 minutes while the battery is beginning to accept a charge. 4. Reduce the charging rate if the battery becomes very warm to the touch or you smell the presence of acid. 5. If the battery emits smoke or dense vapor, greatly reduce the charge rate or turn the charger off. 6. Never touch or disconnect the charger leads from the battery while the charger is on. This could emit sparks that could ignite gases, causing the batteries to explode. When you have completed this segment, you will be able to identify the load tester and describe its function. Recognize the conditions under which load testing is recommended. Recognize the correct configuration for the DMM, the clamp-on ammeter, and the load tester in relation to the battery. You will be able to describe the correct procedure for load testing the battery. You will be able to interpret the results of a load test. This is the 6V4930 Caterpillar battery load tester. You can use it, or the newer 4C4911 Caterpillar battery load tester, to test 6, 8, and 12-volt lead-acid batteries. Both testers are designed to simulate the demands imposed on the battery during operation. Performing the load test can help you decide whether a battery is good or bad. Load testing a battery requires that you measure the current draw placed on the battery and the voltage of the battery at the end of the test. If the load tester you are using does not incorporate the required current and voltage measuring instruments, use the digital multimeter and clamp on ammeter with it to measure the current draws and voltage. Before load testing a battery, perform a battery state of charge test and charge the battery if necessary. Always inspect the battery before performing a load test. Do not load test a battery if it has a loose post or a cracked case, or if the fluid level of any of the cells is below the top of the plates. Make sure the battery is not frozen. Do not load test a battery that has ice in any of its cells. There are 4 steps to load testing a battery. Prepare the battery load tester. Determine the test load to be used. Perform the load test. Compare the results with a minimum acceptable voltage under load for the battery. One, turn the load tester control knob to the off position. 2. Connect one load tester lead, red clip of 4C4911, to the positive plus battery post. 3. Connect the other load tester lead, black clip of 4C4911, to the negative minus battery post. And when not using tester 4C4911, 4. Connect a DMM to the battery to read battery voltage. 5. Clamp an ammeter on either load tester lead to read current draw. Note, the lowest acceptable battery temperature for a load test is 50 degrees Fahrenheit, 10 degrees centigrade. Any battery below this temperature must be warmed to this temperature or greater before a battery load test is performed. The correct test load for a battery is 1/2 the cold cranking amperes, CCA, rating of the battery. For example, a battery with a cold cranking amperes rating of 950 amperes would be load tested at 475 amperes because 950 divided by 2 equals 475. The CCA rating of Caterpillar batteries varies from 450 to 1250 amperes. In many cases, the CCA rating is printed on the battery. One, turn the load control knob clockwise until the ammeter reading reaches 1/2 the cold cranking amperes rating of the battery and keep the knob adjusted to that reading for 15 seconds. 2. After 15 seconds, check and record the DMM voltage reading. 3. After checking the voltage reading, turn the load knob counterclockwise to the off position and disconnect the test equipment. Conduct a load test. If the voltage reading does not meet these minimum requirements and the battery was fully charged before the load test, the battery is probably bad. These are the minimum acceptable voltage readings for the battery specified. 12-volt battery, 9.5 volts. 8-volt battery, 6.3 volts. 6-volt battery, 4.7 volts. When you have completed this topic, you will recognize how to repair electrical connectors. When you have completed this segment, you'll be able to identify characteristics common to all connectors, identify the unique features of each of the three connectors currently in the field, distinguish visually between the three types of connectors, identify the appropriate application for each connector type. There are a number of different types of connectors designed for different uses. All connectors, however, have some characteristics in common. Illustrated here are mating halves, 1, locking mechanism, 2, removable contacts, 3, and mating guide, 4. Connectors have two halves that fit together in a specific way so that the two halves cannot be connected incorrectly. Usually one half has pin contacts, 1, exclusively, and the other has sockets, 2, that mate with the pins. The half with the pins is called the plug, and the half with the sockets is called the receptacle. However, there are some connectors in which both halves of the connector have both pins, 1, and sockets, 2. The two mating halves of a connector are held together by a locking mechanism to prevent the halves from accidentally coming apart. This locking mechanism may be built into the connector, 1, or it may be a clip, 2, that is fastened to the outside of the connector. Most connectors are made so that the contacts can be removed and replaced individually. This prevents having to replace the entire connector when only one contact may be bad. The two halves of a connector are designed so they cannot be put together the wrong way. Some connectors have a tongue, 1, and groove, 2, arrangement that must line up before they will go together. Other connectors are restricted from being put together incorrectly by their shape and the arrangement of their pins and sockets. The pins, 1, and sockets, 2, in a connector are extensions of the wires, 3, to which they are connected. When properly mated, the outside surfaces of the pins touch the inside surfaces of the sockets to provide paths for the electrical current from one set of wires to another. All connectors have some resistance to the flow of current. This resistance is caused by microscopic imperfections, tiny peaks, 1, and valleys, 2, in the surfaces of the contacts, reducing the amount of contact between the pin and socket, and by contaminants and corrosion that eventually occur due to the harsh environments in which Caterpillar machines frequently work. To reduce the corrosion and increase the amount of contact between the pins and sockets, the surfaces of the pins and sockets are plated. These softer plating metals tend to reshape against the connecting surface. This improves their electrical contact. There are three main types of connectors used in Caterpillar products. Each type has its own unique features. The Deutsch connector is circular and made from plastic. It has soft rubber around the wire cavity holes to seal out moisture, dust, or other dirt. This connector comes in three sizes. 3, 5, and 9-pin connectors are commonly found on Caterpillar machines. Each Deutsch connector contact can take two different sizes of wire. The Deutsch connector gives reliable service in harsh environments. It is well sealed, easily serviced, and easily repaired with simple hand tools. The SureSeal connector features housings that are specially molded to guide their connection and provide easy mating between halves. The SureSeal connector provides up to 10 pin and socket connections. The CE connector consists of 1, a metal shell, 2, a plastic insulator, and 3, the contacts. The metal shell halves engage and lock with a quick-turn bayonet coupling. They also have a visual indicator that tells you the two halves are properly mated. The connectors are environmentally sealed with a gasket. The individual wires have sealing grommets. Sealing plugs are inserted into unused sockets to keep out dirt and moisture. Caterpillar engineers make their selection of connectors after careful consideration of numerous application and environmental conditions. Factors influencing selection of a connector for its various applications include maintenance, aging, durability, contact retention, vibration, insulation resistance, contact resistance, thermal shock, temperature life, fluid resistance, water immersion. When you have completed this segment, you will recognize the potential problems of improper tool selection and use. Be able to identify the tool used to extract and insert each of the three connector types. Be able to identify the tool used to crimp each of the three connector types. Be able to identify the appropriate tools used to assemble and disassemble each of the three connector types. Recognize why cleaning is not an efficient approach to repairing a connector. Recognize the procedures for removing and installing contacts in Deutsch, SureSeal, and CE connectors. Proper tools and repair procedures are important. Using the wrong extraction or insertion tool can damage contacts or keep the contact from making a good connection. Using the wrong crimping tool may result in a poor connection between the contacts and the wire. This section describes the special tools and repair procedures for each of the three connectors. Extraction tools for the Deutsch connector are available in two different sizes. The size of the tool you use depends on the size of the wire. These tools look like the CE connector contact extraction tools, but they are not interchangeable. If you attempt to use a CE connector tool on a Deutsch connector, you are likely to break the tool. The tools are color-coded to help you identify them. Notice that the 16 to 18 gauge 1 Deutsch tool is blue, and the 14 gauge 2 Deutsch tool is dark green. The CE connector tools have different colors. No special tool is required for inserting new contacts. The CAT 1U5804 hand crimp tool is used to crimp the Deutsch connector contacts to the wire. This tool can also be used to crimp the CE 12 to 18 gauge connector contacts. The tool has a wire size selector. You set the wire size selector to match the gauge of the wire to be crimped. Select the correct size tool for the size of the wire you want to remove. Slide the tool along the wire until the tool tip snaps onto the wire. Push the tool into the connector until you feel it release the locking fingers inside. Do not turn the tool during release of the fingers. This can destroy the fingers or break the tool. Pull the wire from the connector. Cut the old contact from the wire. Remove the insulation from the wire to a length that will allow the wire to be visible through the inspection hole in the side of the contact, and leave no more than 1 1/2 millimeters or 1/16 of an inch of bare wire extending from the barrel of the contact. Align the selector knob on the side of the crimping tool to the wire size to be crimped. Insert the contact into the crimping tool and turn the adjusting screw until the end of the contact barrel is flush with the surface of the tool. Insert the wire into the barrel of the contact. Crimp the wire in the contact by squeezing the handles of the tool together until the handle hits the stop. Grasp the contact about 25 millimeters or 1 inch behind the contact's crimped barrel. Push the contact straight into the connector grommet until a definite stop is felt. Tug slightly on the wire to be sure the contact is locked in place. Caterpillar has 4 sizes of extractor tools for the CE connector. You select the tool based on wire gauge in the connector. These tools look like the Deutsch connector contact extraction tools, but they are not interchangeable. The tools are color-coded to help you identify them. Notice that the 16 or 18 gauge CE tool is black, 1. The 12 to 14 gauge tool is yellow, 2. The 8 to 10 gauge tool is light green, 4. And the 4 to 6 gauge tool is gray, 3. No special tool is required for inserting new contacts. 2 different crimping tools are required for service on the CE connector. The CAT 1U5804 hand crimp tool, 1, is used for crimping 12 to 18 gauge contacts and is the same tool that is used to crimp Deutsch connector contacts. The CAT 4C4075 hand crimp tool assembly, 2, is used with 2 retainer assemblies, 3, for crimping 4 to 10 gauge contacts. Cut the old contact from the wire. Remove the insulation from the wire to a length that will allow the wire to be visible through the inspection hole in the side of the contact, and leave no more than 1 1/2 millimeters or 1/16 of an inch of bare wire extending from the barrel of the contact. Bolt the correct retainer assembly on the crimping tool. Insert the contact into the retainer assembly and close the jaws far enough to hold the contact. Insert the wire into the barrel of the contact. Crimp the wire in the contact by squeezing the handles of the tool together until the handle hits the stop. You do not need a special tool to remove contacts from the SureSeal connector. However, you do need this special tool for inserting a new contact. For SureSeal connectors, use the Caterpillar crimping and stripping tool 6V3001. This tool was selected after extensive comparison of general-purpose tools. Remove the contact by pulling on the wire fastened to the contact. If the wire is too short, use needle nose pliers to remove a pin contact. Use a blunt rod to push a socket contact out of the connector that is not connected to a wire. Cut the old contact from the wire. Remove 4 to 5 millimeters or approximately 3/16 of an inch of insulation from the wire. Put the smaller U opening of the contact in the smaller opening of the tool with the open side of the U toward the double arc edge of the jaw. Insert the wire into the opening of the contact. Crimp the wire in the contact by squeezing the handles of the tool together until the handle hits the stop. Put the larger U opening of the contact in the larger opening of the tool with the open side of the U toward the double arc edge of the jaw. Crimp the contact around the insulation of the wire by squeezing the handles of the tool together until the handle hits the stop. Push the tool into the connector body until it's completely through the body. Pull the plunger of the tool back so that it is retracted into the tube of the tool. Push the new contact into the tube of the tool until it stops against the retracted plunger. Remove the tool by grasping the body of the connector to keep the contact in place and pulling the tool out of the connector. Upon completion of this topic, you will be able to recognize the normal operation of a typical CAT lighting system. Recognize the benefits of a typical CAT lighting system. When you have completed this segment, you will be able to identify and state the function of the components of a typical CAT lighting system. Every Caterpillar machine is equipped with a lighting system. Depending on the machine, this system may include flood lamps, tail lamps, flashing warning lamps, dash lamps, and indicator lamps. Let's look at some of the components of a typical Caterpillar lighting system and then see how these components are connected. The battery disconnect switch lets you manually disconnect the negative terminal of the batteries from the circuit when required. When the switch is in the off position, all circuits are open and current cannot be drawn from the battery. Two 12-volt batteries power the starter motor and establish normal system voltage. A circuit breaker limits the amount of current allowed to flow through the circuit. The main relay acts as a normally open switch activated by current from the key start switch. A fuse protects each lighting circuit. One or more switches are provided to turn lamps on or off. Wiring harnesses route power to the lamps. A connector serving both lamps facilitates manufacturing and servicing the circuit. Two lamps connected in parallel use the circuit's power to produce light. These technicians are using a schematic diagram to trace the lighting circuit. They are following the current path from the batteries and locating the various components of the circuit. In this module, you will use a simplified lighting circuit schematic to explore circuit faults and practice troubleshooting skills. Here is the simplified circuit. Like the one you just saw, this model lighting system includes the following components. 1. The battery disconnect switch, which opens the connection from the battery negative terminal to all electrical circuits. 2. Two 12-volt batteries, which power the lighting system and establish normal system voltage. 3. A circuit breaker, which provides overcurrent protection on power distribution wires. 4. A key start switch. 5. A relay which provides the shortest path for heavy current and keeps the heavy current from flowing through the key start switch. 6. A fuse, which provides additional protection for each circuit in the lighting system. 7. The lamp switch, which provides operator control of the lamps. 8. Wiring harnesses. 9. A connector which routes power to the lamps. And 10. Two flood lamps. The Caterpillar battery disconnect switch secures all electrical systems and the vehicle from unauthorized operation. Extends battery life because parasitic loads such as the alternator regulator are disconnected during extended vehicle inoperation. The Caterpillar battery disconnect switch allows quick removal of battery power to a stuck starter for prevention of electrical harness damage and vehicle fires. Facilitates safe, easy electrical system troubleshooting and servicing using the convenient disconnect point. Caterpillar maintenance-free batteries provide high cold cranking amperage, CCA, and reserve capacity ratings. Heat-sealed cover for prevention of contamination and increased case strength. Lightweight, high-impact strength polypropylene case. Caterpillar maintenance-free batteries provide PVC or polyethylene separators for better vibration resistance and better protection against shorts than paper separators. Anchored elements for vibration resistance. Higher density paste for better vibration resistance and deep cycling. 45-degree tilt capacity to help prevent corrosion-causing spillage in rough terrain applications. Caterpillar maintenance-free batteries provide centered plate strap and through partition connectors which provide the shortest electrical path for maximum starting power. Die-punched lead grid which resists damage caused by acid attack, overcharging, and gassing. Built-in flame arrestor vent, which reduces possibility of explosion from an externally produced spark. The Caterpillar circuit breaker protects wires from damage due to high currents, a direct cause of fires. Tolerates high transient currents associated with electrical motor startup. Replaces multiple fuses, decreasing power system complexity and increasing reliability. The Caterpillar circuit breaker returns vehicles to productive operation more quickly than fuses, using the resettable feature. Reduces the likelihood of altering the overcurrent protection value, as happens when a fuse is replaced with a fuse having an incorrect rating. Matches current load requirements by virtue of the variety of ratings available. The Caterpillar relay is more reliable than a switch in this application due to superior switching action. Sized to meet continuous requirements of switched loads. The Caterpillar fuse protects against overcurrent, a direct cause of fires. Protects against wire damage caused by direct shorts to ground. Is sized according to current requirements for the load supplied by each power distribution wire. The Caterpillar switch provides these benefits: heavy duty for longer life, high cycle life, environmentally protected, uniformity with other systems for reduced parts inventory. Caterpillar wiring harnesses provide selection of wire gauge according to the rating of the fuse or main breaker that supplies power to it. This technique prevents a short to ground from destroying wire insulation before the fuse blows or the breaker trips. Caterpillar wiring harnesses provide nylon braid, which protects the wires against abrasion, reducing the chance of shorts. This braid is resistant to all engine and vehicle fluids over the vehicle operating temperature. Caterpillar wiring harnesses provide reduction of harness wear points, a vehicle fire source, by controlling harness routing with chain link and tie wrap, general routing, bolt-on clips, general routing, or steel conduit, battery cable routing. Easy servicing and troubleshooting using circuit numbers hot-stamped on wire insulation, which relate each harness wire to the electrical schematic, are benefits to the wiring harness as well. Caterpillar connectors provide convenient disconnect points for safe and easy servicing and troubleshooting of the electrical system. Caterpillar halogen flood lamps provide these benefits: greater efficiency than older type incandescent lights with 30 to 35% more light from the same power input. Greater visibility resulting from a whiter, brighter light output. Constant output over bulb lifetime. Convenience of one small, portable, low-cost bulb fitting all lamp sizes. The benefits of the Caterpillar key start switch include high current rating, a 24-volt control terminal for electronic controls that need to know the key switch position status, protection from unauthorized vehicle operation, a convenient operator engine off on machines equipped with electronic engine shutdown modules. When you have completed this segment, you will recognize normal current flow in a typical Caterpillar lighting circuit with the switch on. Recognize the normal current flow in a typical Caterpillar lighting circuit as represented on the digital multimeter. As with many Caterpillar lighting circuits, some components of this circuit are connected in series, while others are connected in parallel. The parts of this circuit are identified as follows: disconnect switch, 1. Batteries, 2. Main breaker, 3. Main relay, 4. Fuse, 5. Wiring harness, 6. Lamp switch, 7. Connector, 8. Flood lamps, 9. Key start switch, 10. These components are connected in series. The current flowing through them is a combination of the currents flowing in the parallel branches of the circuit. 1. Disconnect switch. 2. Batteries. 3. Main breaker. These components are connected in parallel. They provide 3 separate paths or branches to ground for the flow of current. Each branch conducts a portion of the total current flowing through the circuit. Added together, the individual branch currents are equal to the current flowing in the series part of the circuit. 4. Main relay. 5. Fuse. 6. Wiring harness. 7. Lamp switch. 8. Connector. 9. Flood lamps. 10. Key start switch. Current in this lighting circuit flows from the battery positive terminal through the circuit components and ground, machine frame, to the battery negative terminal. 1. Disconnect switch. 2. Batteries. 3. Main breaker. 4. Main relay. 5. Fuse. 6. Wiring harness. 7. Lamp switch. 8. Connector. 9. Flood lamps. 10. Key start switch. In order for any current to flow in this circuit, all 3 switches must be closed: the battery disconnect switch, the key start switch, and the lamp switch. If any one of these switches is open, no current will flow. 1. Disconnect switch. 2. Batteries. 3. Main breaker. 4. Main relay. 5. Fuse. 6. Wiring harness. 7. Lamp switch. 8. Connector. 9. Flood lamps. 10. Key start switch. The battery disconnect switch controls power to all electrical circuits in the machine. When it is open, no current can flow in the lighting circuit. The main relay controls power to all lamp circuits. Machines with several lamp circuits, flood lamps, dome lamps, stop-tail lamps, often have separate switches to control each circuit. But unless the main relay is closed, no current can flow in any of these circuits, and none of the lamps will operate. This switch controls current flow to the flood lamps. In this circuit, even if the key start switch and battery disconnect switch are closed, no current will flow through the lamps unless the lamp switch is also closed. When all 3 switches are closed, current normally flows as shown. The main breaker, main relay, fuse, lamp switch, and connecting conductors form a common path. Past the lamp switch, the current separates into 2 parallel paths, flowing through harnesses A and B and the 2 flood lamps. Under normal conditions, the amount of current flowing in this circuit is limited by the resistance of the flood lamps. Resistance will vary depending on the temperatures of the lamp filaments. In this 24-volt system, the resistance of the lamps holds the total current to well below the 10 amperes for which the fuse is rated. The other components of the circuit offer little or no resistance in normal operation. Certain types of faults in this circuit will cause a larger than normal current flow. Here, a short to ground has occurred between the lamp switch and the lamps. The blown fuse has served its purpose by preventing the continued flow of excessive current which could damage the circuit. Depending on the location of the fault, either the fuse or the main breaker will protect the circuit. You can use the DMM to help determine whether the lighting circuit is operating normally. To use the DMM in this way, you must be able to recognize normal and abnormal DMM readings. One of the most valuable measurements you can make is a voltage drop measurement. Voltage drop measurements also often require less work than other measurements. They can usually be made easily anywhere in the circuit, and they do not require you to break the circuit. By comparison, current measurements are more difficult. They require you to measure where you can conveniently break the circuit, at the lamp switch, for example. Resistance measurements, too, are not as convenient. They require you to turn off power to the circuit and isolate the part you're going to measure from other parts of the circuit. Voltage drop readings across the components in this circuit can tell you whether or not it is working normally. Voltage drop is the difference in electrical potential, or voltage, that results from current flowing through a resistance. Voltage drop represents the energy loss across a load. In this example, the voltage drop between test points 1 and 2 is 0. A voltage drop of approximately 0 volts across the main breaker with both lamps lit indicates normal breaker operation. Current is flowing through the breaker, but with little or no resistance. Likewise, a voltage drop of about 0 volts across the main relay with all switches closed and both lamps lit indicates normal relay operation. Current is flowing through the relay, encountering little or no resistance as it does so. A voltage drop of approximately 0 volts across the fuse with all switches closed indicates normal fuse operation. Current is flowing through the fuse, but with little or no resistance. A voltage drop of about 0 volts across the lamp switch with all switches closed indicates normal operation. Current is flowing through the lamp switch with little or no resistance. Normally, with the switch in the off position, a potential of approximately 24 volts exists across the open switch. The same voltage should exist across any pair of test points on opposite sides of an open in this circuit. In this 24-volt system, a voltage drop of approximately 0 volts across wiring harnesses A and B with both lamps lit indicates normal operation. Current is flowing through the wiring harness and connector with little or no resistance. Upon completion of this topic, you will be able to analyze a typical Caterpillar lighting circuit to the fault identification level. When you have completed this segment, you will be able to identify the 4 basic electrical faults in a typical Cat lighting circuit. Recognize the effect of an open, resistance, short, and short to ground in a typical Caterpillar lighting circuit as represented on the DMM. Predict changes in behavior and DMM readings as a result of opens, resistance, shorts, and shorts to ground in the circuit under test. Interpret changes in DMM readings as a result of open, resistance, short, and short to ground in the circuit under test. Problems in Caterpillar lighting systems may be caused by an open, symbol number 1, resistance, 2, short, 3, or short to ground, 4, fault in the circuit. These symbols are used to represent the 4 types of faults. This is the symbol for an open fault. An open in a circuit is a complete break in the intended path for current flow. Because it stops current flow, an open fault prevents the circuit from working properly. This is the symbol for a resistance fault. Some circuits will not work properly if there is even a small amount of extra resistance in the circuit. Other circuits can tolerate more resistance. A small amount of extra resistance in a lighting circuit may not dim the lights noticeably, but as the resistance becomes larger, the lights will dim or go completely out. This is the symbol for a short. A short is an unintended electrical connection within a circuit which provides an additional path for the flow of current. A short can have little or no resistance, dead short, or a significant amount of resistance, resistive short. A short in a lighting circuit will prevent the circuit from working properly. This is the symbol for a short to ground. A short to ground is an unintended electrical connection between a point in a circuit and the machine frame. A lighting circuit with a short to ground will not behave normally or may not work at all. The effects of these faults can be shown using the same lighting circuit that was used in the previous topic to show normal operation. The components of this circuit are the disconnect switch 1, batteries 2, main breaker 3, main relay 4, fuse 5, wiring harness 6, lamp switch 7, connector 8, flood lamps 9, key start switch 10. Here, a short to ground has occurred in the circuit between test points 6 and 7. What symptoms of this fault can you observe? Notice that the lamps are no longer lit. The short to ground may also have caused the 10A fuse, located between test points 5 and 6, to blow. The fuse looks fine in the diagram. How can you tell whether it's blowing? When trying to locate faults in this circuit, remember that faulty components may appear normal on the screen. Even a switch, relay, or circuit breaker that seems to open and close properly when you select it may have a problem which prevents normal circuit operation. To be sure that a component is faulty, you will usually have to make measurements. If a lamp is shown on the screen to be illuminated, you can be sure that it works. But if a lamp does not illuminate when it should, do not rush to conclude that the lamp is defective. Some other problem, for example an open in the wiring harness, may prevent the lamp from working normally. Again, you must rely on measurements to locate the fault. When there is an open in a circuit, current stops flowing and the circuit will not operate. With all switches closed, the DMM voltage reading between these points in the circuit should be approximately 0 volts. With an open of infinite resistance in the circuit, however, all current flow has stopped and the full battery voltage is dropped across the open. In this case, it is 25.2 volts. Here, an open has occurred in the parallel part of the circuit for lamp A. Lamp B continues to operate while lamp A does not. Note that the flow of current is being interrupted in only one wire. In this circuit, a short is creating an unintended current path in the lamp switch. This allows current to flow even when the switch is open. As a result, the lamps stay on even though the lamp switch is in the off position. With the lamp switch open and the other switches closed, the DMM reading across these test points would be 25.2 volts. The reading here is 13.4 volts because of a resistive short in the switch. Here is a circuit with a resistive short across the main relay contacts. The key start switch is off, the lamp switch is in the on position, and some current continues to flow through the short in the relay. As a result, the lights remain dimly lit. A low resistance short to ground in the circuit makes the circuit inoperable. No current flows through the lamps. As a result of the short to ground, current immediately takes the path of least resistance through the fault back to battery negative. Without the resistance of the lamps to limit current flow, the short to ground also causes current to increase to a level not intended for the circuit and causes the fuse to blow. If the short to ground had occurred to the left of the fuse, the main breaker would have tripped and all current in the circuit would have stopped. The fuse would not be affected even though it has a lower rating than the main breaker because the short to ground occurred before the fuse in the current path from battery to ground. Under normal conditions, with no power to the circuit and the lamp switch open, the resistance reading between test point 6 and ground would be OL, overload. With a short to ground between test points 6 and 7, the reading shows the resistance of the short. It is more effective to take a resistance reading in this case because the fuse is blown and there is no voltage at test point 6. When there is a resistance in a circuit, current flow is reduced. If the resistance is large enough, the lights will dim or go completely out. With all switches closed, the DMM voltage reading between these points in the circuit should be approximately 0 volts. However, with the resistance in the circuit, current flow has decreased and a portion of the full battery voltage is dropped across the resistance. In this case, it is 7.4 volts. In this segment, you will troubleshoot 3 separate lighting circuit problems. Questions and instructions will guide you as you work through the problems. Each of the following exercises begins with the description of a problem one of your customers is having with the Caterpillar machine. Here are some things to remember as you complete these exercises. The exercises in this topic guide you through the troubleshooting process. For this reason, you will only be able to operate a component of the circuit or take a measurement in this topic when asked. In some steps, you will be asked to open or close a switch or the connector. When you are asked, the appropriate symbol is active, and you'll be able to open or close the switch or the connector by selecting the schematic symbol for that component. In other steps of these exercises, you will be asked to use the digital multimeter to make a measurement. When you are asked, the DMM symbol is active, and you will be able to operate the DMM by selecting it. In the real world, the resistance of a lamp varies depending upon the temperature of the lamp filament, but in these exercises, the normal resistance of each lamp will be a constant 9.6 ohms. Use your knowledge of electricity and your understanding of the Caterpillar lighting system to follow the logic of how these problems are being solved. You are now ready to begin the guided troubleshooting practice exercises for the Caterpillar lighting circuit.